Hey guys, I'm Kashup, and this is a video of how I approach the weekly contest 420 for LeetCode. The final standing for this contest I think was 700 and something. Right. So the final standing for this contest was 740 out of 32,561. That's pretty good. I did them in C++, except for Q3, and I'll talk about Q3 later and how I did it. But for now, we'll go over Q1, Q2, Q4, as well as Q3, how I approached them and how I solved them. We'll walk through them, and I'll just kind of give like a brief explanation. Sometime later in another video, I'll actually write the code and go like the actual logic of it. So the final rating for this contest was 1851. It might go up after flag checker runs. So here's Q1. You're given a string target. Also going to type target on your computer using a special keyboard that only has two keys. Key 1 appends the character A. Key 2 changes the last character of the string on the screen to its next character in the English alphabet. For example, C changes to D and Z changes to A, right? So it's just +1, right? Pretty simple. If you have all the alphabet, if I have all the alphabet, right? And then, alphabet of A, you can just change it to alphabet of A plus 1. So you can also do like a circular array kind of thing. So, you have A over here, you have Z over here. So this turns into this, and then this goes into B, so on and so forth, ... right? You can do that kind of thing, right? And here's how I did it. So you can start off the function by preparing for action, right? It creates an empty list, right? We're going to create an empty list, right? To hold the sequence of the strings, okay? And then we're going to create a string cur, right? We're going to call a string cur with A as a starting point, okay? And now this A string is added to the result list. So now the result list, all right, this is going to be result is equal to A. So now our current result array looks a little something like this. That's what it looks like. After that, we can iterate over our target string, right? Now it's going to look through each character in the target string one by one, right? And this is our target string, one by one. After which, if the current character is the first one, for example, I is equal to 0, and it's already A, the string A, right? It's already A. Then we can skip the transformation and we can move on. We don't need to change anything. And if the loop reaches a position beyond the current length of cur, right? If it reaches beyond the current length of this, it's going to append A to this. So, cur is going to become AA. So cur A turns into AA. Afterwards, we're going to extend the string to match the growing length of this target. And each time this happens, the new string is added to the result, right? So we're just going to use a pushback, result.pushback. So it's a result. We can use a result.pushback, right? Push underscore back of cur. And this is in C++. Okay, so this is dot pushback as for C++. And the next step is, if the last character in this cur doesn't match the corresponding character in target, we can enter a loop to change the last character, starting from A and incrementing it until it matches the target character. Each new string after the change is added to the result. Make sense? This continues until our cur matches the target string, right? So we start off, like we check the last character in cur, or over here it'd be A. And if it doesn't match with the corresponding character in target, right? If it doesn't match with target of I or whatever it is, if cur of I is not equal to target of I, right? We're going to enter a loop to change the last character starting from A, incrementing it until it matches the target character, right? So we just have to change it until it goes to target. Finally, once the entire target string has been processed, the function returns a list of strings, which then shows the progression from A to the target string. So as we can see, this is our progression from the A to the target string. So we do all this operation in order to go from A to ABC, right? So this is the whole process of it. And you can see in the explanation, they did the same thing. So this is my C++ code for it. I'll make sure to post the solution on the GitHub, and I'll put the GitHub link and repo in the description below. You can go check that out. So if you guys have any questions for Q1, just post it in the comment section below. I'll talk about it. So next one is Q2. And Q2 was count substrings with frequency, k frequency characters 1. Now the weird one was that, it just said 1, but there wasn't a second part. So I'm going to assume that sometime later in a different contest, they're going to have it. All right, and if they don't, well, it's just going to be kind of weird, right? C++. Just going to make sure this is the right one. Okay. So given a string s and an integer k, return the total number of substrings of s where at least one character appears at least k times. A substring is a contiguous non-empty sequence of characters within a string. So we're going to walk through this. If you don't understand that, just go back, take a second to read it and understand it. So, so we can first initialize so we can set up the stage. So we're going to calculate the len of the string s and store it in n. So, we can set n, right? Or that's a bad one. Right? So we can set n. N is equal to len of s. And this is a really simple language. It's like Pythonic language. But we're going to initialize the variable result to 0. So we're going to set result is equal to 0, right? And then we'll eventually hold the total number of valid substrings. So this is going to change, right? So plus plus, right? Depending on how many valid substrings there are. After that, we're going to do an outer loop. So we're going to loop over all possible substring lengths from 1 all the way to n. So we start off in, range of 1 to len of s, or you can just say substitute this for n because we already have it over here. Great. And then with we're going to use the outer loop to determine the length of the substrings it's going to explore. So this right here. So while len is length, then n. Oh, change something there. So yeah, this is our outer for loop, and this is our inner for loop. There's another for loop here, so this is just n squared. But our outer for loop is pretty simple. It's just going to loop through it to determine the length of substrings that we're going to explore. And then after that, for each substring length, a frequency array or F for EQ, frec, whatever it is, of size 26, right, is equal to size of 26. I'm just going to write it in like simple language. Right? And this is to track the frequency of each letter from A to Z. So this goes from A to Z. Okay? And it is initialized to zeros. Okay, so this frequency array of size 26 is initialized to zeros. And then the inner loop, which is this one, inner loop, pretty simple. And the first part of this inner loop takes the first len characters from S and populates the freq array with their frequencies. Then the function checks if any character in the frequency array has appeared k or more times using this helper function over here, has car with frequency of k, right? And if this condition is satisfied, right, this thing right here, so if this is true, then the result is then incremented, right? See over here. So if the helper function, when we run it with frequency comma k, if this is true, if it returns true, right, if this if statement is correct for this for loop, then we're just going to increment the counter by 1. I mean over here, we increment the counter by 1. And that is the first for loop. The second for loop, we're going to use a sliding window. So we're going to use a sliding window to consider each subsequent substring of the same length. And for each new position of the string, we're going to update the frequency array by adding the count of the new character that enters the window. Okay, so we're going to update this frequency array. So this frequency array, we're going to add the count of the new character. So the count, so how many of them are there? And they're going to remove the count of the old character that has moved out of the window. So we have our sliding window, right? If our array looks a little something like this, just an example kind of thing, we use a sliding window. So we're going to check this, right? Move this, slide it over to here, slide, right? And then similar thing over here, where we slide this window across the whole array, changing it by 1 every single time. So we're going to remove the count of the old character that has moved out of the window. So every single time we move it, we remove the count of the old one. And we're going to check if any character in this window that we're currently checking, and this window can have different lengths, right? It can have a length of, like a length of 2. Right? It can be a mutable thing. It can change, right? Sometimes windows can be of length 3. Sometimes they can be of length 2. Right? It really depends. We're going to remove the count of the old character that has moved out of this window. And then we're going to check if any character in this window has a frequency of k, again, with our helper function over here. So this is our, this right here is our sliding window. Right, this is our inner loop, the second part of it, and we're going to use a sliding window over here. And then we're again going to call our helper function over here. Same thing over here, same as before over here, except it's just here. We're going to use a sliding window instead of normal way. And then finally, we're going to return the result, right? Returning this result for this function over here, which finally is the total number of substrings where at least one character appears k times, right? So as soon as this gets satisfied, we're going to return this result. And that result should be our answer. Okay. Next up is the Q3. I'll go over that real quick. So the bad thing about Q3 was that there's all the stuff for Q3, right? And then I had just one solution that worked. And I submitted the solution at exactly 12 o'clock. Or, well, 12:01. So the contest was ended by then. And I didn't get the solution in, so I didn't have the AK, which is unfortunate. But yeah, here's Q3. You're given an integer array nums, and any positive divisor of a natural number x that is strictly less than x is called a proper divisor of x. For example, 2 is a proper divisor of 4, while 6 is not a proper divisor of 6. You are allowed to perform an operation any number of times on nums, right? Our sample over here. Where in each operation you select any one element from nums and divide it by its greatest proper divisor. Return the minimum number of operations required to make the array non-decreasing, so ascending order. If it isn't possible to make the array non-decreasing using any number of operations, we return -1. Okay, pretty easy to understand. So once you get that question down, we can start off over here. So the first step is that we can begin by preparing some crucial elements, right? Some really important elements for this problem. And we're going to define a constant max limit, right? This thing right here, to 1 million, right? And it's going to initialize an array divisor array, this thing right here. And we're going to set it to max limit +1. In order to store the smallest divisors for each number. And this is an integer array, okay? And then now we're going to pre-compute a flag, and it's going to be set to false. We're going to pre-compute this flag, indicating that the divisor array has not yet been filled. And our next step is to compute our smallest prime divisor, or, well, GPD, greatest prime divisor. Greatest proper divisor, sorry, not prime. So we can use our compute GPT helper function over here in order to compute our greatest proper divisor. And before we perform any operations, we're going to call this function compute GPT to GPD to compute the smallest, greatest proper divisor for every number up to max limit, which over here was right our number 1 million. Then we're going to start off from I is equal to 2. Boom, right here. And for each one of I, right, for each I multiple, or not multiple, for each I, so 2 times I, 3 times I, so multiples of I, they're updated in the divisor array with I, marking I as the smallest prime divisor, or greatest, smallest prime divisor for those multiples. Yeah. Once the divisor array is filled, the is pre-computed flag is pre-computed, right? So this is pre-computed flag is going to be set to true. So once this is finished, this is going to be set to true. And that's going to show that the GPT, the greatest proper divisor, has been pre-computed and no further calculation is needed or necessary. And after this is going to be our core logic. So once we're done with all the pre-computation we needed to optimize this thing, we can get to doing the actual work. And this is the actual minimizing the operations. And this is the main logic for it. This is the main logic for it. So we have our input array nums, this thing right here. So, wrong side. So this is our input array of nums. And it's going to be copied to a new array, modifier array, so this thing. And we're just copying it. And it's going to be of length nums.length. And this is to prevent any altering of the original input. So this is not in place. We're just copying our nums array, and we're not going to modify it in place, just to make sure, just to keep it safe. Right? That's going to be for testing later on. We're fine. Great. So now that our total operations is initialized to 0, right? So total operations right here, we're going to put that to 0. And this is going to hold the count of the total operations needed in order to perform and make this array non-decreasing, or just not make it at all. The next step is to traverse the array in reverse. That's right here. So we're going to iterate through the array from the second to last element, so n minus 2. So we start off at n minus 2. So we're going to go from second to last, which is n minus 2. And n is the len of the array. Okay? So we're going to go from the second to last element down to all the way to the first element. So this is going to go to the first element. Okay? Of index 0. So I is equal 0. And then this reverse traversal is going to make sure that each element is compared to the next one. After this, we're just going to check if it is greater. So for each element in our modified array of I, so this thing, our copy of nums. So we're going to make sure that each one of these elements is greater than the next element. And if it is, so we're going to make sure that each element in modified array, we're not going to make sure, but we're checking if modified array of I is greater than array of I plus 1. Okay? And then this function is going to enter a loop where it's going to keep dividing this modified array of I by its smallest divisor. And we're going to keep on dividing this until it becomes smaller than or equal to the modified array. So this is going to happen. This process is going to keep on repeating until is equal to or smaller than or equal to modified array of I plus 1. Make sense? And the fifth step is to, inside our loop, the divisor of modified array of I, so that's this thing, or this final step over here. If this divisor is 1, this means that the modified array of I is prime and it cannot be reduced any further by its smallest divisor. And that's because for any prime number, right, for any prime number, its smallest divisor is 1. All right, we take 2. This smallest divisor is just 1, so 2 divided by 1 is equal to 2. And since these are the same, we're not going to get any different solution anytime. So, so as soon as it becomes prime and it cannot be reduced any further, we're going to return -1 since it's impossible to make this array non-decreasing with the available divisors at our hand. But if a divisor is found and the element is divided by it, and the total operations count is incremented. Okay. So we had our total operations over here. We had it set to 0. And so in this case that we are able to divide it, we're going to increment this total operations by 1. Okay. Makes sense? Yeah. I think that's about it for this question. Yeah, and then, if it's less than 0, then we just return it because it's not possible. And then we just return our total operations count. Simple as that. This one really messed me up because halfway through the contest, I had this error where it just said like error rendering component, and so I couldn't get the test cases to run, so I had to directly submit it, and that kind of like wasted most of my time. I wish I didn't do that, but I kind of had to. No idea why that happened. It happened for every language I tried. I tried C++ and I tried Java, tried Python. It didn't help at all. But yeah, that's Q3, and here's Q4. So Q4 is check if DFS strings are palindrome. This one really didn't take me much time because it kind of makes sense to me. I found this algorithm. Oh yeah, also for Q3, people use sieve in order to get their prime numbers. And it makes sense, and they only computed all the way to 1,000. Someone on the Discord server for, I think it was Kiki Impact. I'll put it in the description below so you guys can join it. But someone just searched up the first 1,000 primes, which makes sense because that's valid to use, right? You can do that. That makes sense, right? So they just pre-computed the first 1,000 primes, or they just put in a hash map or an array. I guess they put in an array, and then that should save their time. Some people use a sieve. I use this method where you physically do a computation, but it didn't take much time at all, so it's fine. This question, check if DFS strings are palindromes. So this question really helped me out, and it was kind of easy for me because I found this algorithm. I read about this algorithm somewhere on Wikipedia, like about a month or 2 ago, and I remember about it like in like 20-ish minutes. Figured out the solution for it, and then I took another 20 minutes to write it down. But here's the question. You are given a tree rooted at node 0, consisting of n nodes numbered from 0 to n minus 1. The tree is represented by an array parent of size n, where parent of I is the parent of node I. Since node 0 is the root, parent of 0 is -1. You're also given a string s of length n, where s of I is the character assigned to node I. You consider an empty string DFS string, and define a recursive function dfs_x that takes a node as a parameter and performs the following steps in order. So these are steps in order. We first iterate over each child y of x in increasing order of their numbers and call dfs of y. Then we add each character s of x to the end of the string dfs string. Note that dfs string is shared across all recursive calls of dfs. So this string is shared across every single dfs call. And we need to find a Boolean array of answer of size n, where for each index of I from 0 all the way to n minus 1, so for the whole length of n, or the array, so for the whole length of s string, we need to do the following. We first empty this dfs string, and then we call this recursive function with the parameter of I. And then if our resulting string, dfs string, is a palindrome, then we set answer of I to true. But if it isn't a palindrome, meaning that it isn't the same backwards and the forwards, then we set it to false. And finally, return the array answer. It says over here, it defines what a palindrome is. We know what that is. So here are the test cases. It's kind of makes sense. I can put the algorithm for what I used over here in the description. I'll put the link to it. It's really useful. But here's what I did. 1 second. Okay. So I use C++, and here's what I did. Okay. Ow. Okay, so we begin by setting up our key components, which are, we define the mod multiply function. Mod multiply, right here. Mod multiply. Weird. Oh, found it somewhere here. It's fine. So first of all, we define our mod multiply function to handle modular multiplication in order for us to avoid overflow during calculations. So we can use this mod multiply function, helper function, this thing right here, in order for us to avoid overflow during our calculations for this thing. And we're going to use a method similar to exponentiation by squaring to efficiently compute the product modulo of a given number. Okay. And then the next one was that we can use this main function find answer, this thing right here. Okay. And it's going to accept two parameters. And the first one is an array parent, so this thing. So it's going to accept the array parent. That's going to represent our tree structure and the string s, this thing, in order for us to analyze that. And the next step is for our tree to be constructed. And here's how we can construct our tree. We're going to use the number of nodes, n, and we're going to initialize a 2D vector called children. Okay? And this can hold the child of each node, or the children of each node. And for each node that's starting from the second one, which is index of 1, right, and that's right here. Oh, man. So for each index starting at 1, we're going to populate the children vector based on the parent array. So based on this thing, I'm going to use dot pushback in order for it to be populated. All right, and after the step after that is we're going to use two constants for our hashing, and this is the base and modulo setup. So we're going to use two sets of bases, and mods are defined for primary and secondary hashing. And this is going to help us in creating unique hash values for tree substructures. Okay, so that's all this over here. All this stuff over here. Base primary and secondary, mod primary, mod secondary. After that, we're going to pre-compute our powers. Pretty simple. We're going to pre-compute the powers of the bases. And for that, we're going to use the array base power primary, this thing right here, and our base power secondary. And these are filled with powers of their respective bases, right here. And that's going to be used in the hash calculations that we're going to use soon. Next step for us is to initialize our hash. So we're going to initialize the hash arrays, and we're going to prepare for BFS breadth for a search. So this is going to use 4 hash arrays. The first one is the forward hash primary. If I scroll down, so we're going to have our forward hash primary, reverse hash primary, forward hash secondary, and reverse hash secondary. And these are initialized for us to store the forward and reverse hash values for each node. We're also going to set up an in-degree array in order for us to track how many children each node has. And that's going to help us in the process of BFS. The next step is to actually do the BFS process. And here's how it's going to go. So all the nodes with no incoming edges, so in the degree of 0, they're pushed into the queue for processing. So right here, so this is our BFS queue. So any of these ones that have an in degree of 0 or no incoming edges, we're just going to push them into this cube. After which, we're going to do some hash calculation, right? Hash calculation is pretty cool. And our nodes are processed in the BFS order as such. So for each node, our function is going to calculate the forward hash by combining the hashes of its children. So it's going to take the child and it's going to combine those hashes and its own character from the string of S. And this hash is built using modular arithmetic. So that's why we had our stuff before this. Right? So that's our base and modular setup. That's why this is for. And we're also going to calculate the reverse hash by iterating over the children in reverse order. And then finally, we're going to take both the primary, secondary hashes, and we're going to compute them similarly for each node. The 8th step is for us to do some subtree length calculation, and then it's pretty simple, right? So our function is just going to take the update, it's just going to take the length of the subtree for every single node. And it's going to update it by summing the lengths of its own children, allowing it to build the tree structure from the leaves up all the way to the root. The 9th step is for us to do result compilation. And once all our nodes have been processed, the function checks for palindromic properties. So that's the part over here that said, if the resulting string DFS string is a palindrome, right, that's this part. So we're going to check. Once it's been processed, the function's going to check if it's a palindrome or not. And then it's going to compare the forward and the reverse hashes for both the primary, secondary matches. And if both the pairs match for a singular node, then it's going to mark that node as true in our result vector. And the final step is to return. So in the end, our function is going to return the result vector, which is, over here, whatever we mark the true node as. And that's going to indicate whichever node correspond to palindromic structures based on their hashes. Again, as soon as it finds that palindromic hash or palindromic structure based on the hashes of the children, it's going to change that result vector. And in the end, the result vector gets returned. So this is my code that I wrote in C++ for it. All this is over here. I'm going to upload every single one of these solutions to GitHub. You can go check them out. Yeah, that was the post-contest review for Weekly Contest 420. I hope you guys enjoyed it, and I hope you learned something from it. Thank you for watching, and I'll see you in the next one. Holy shit, that took way too long. 33 minutes. Oh my god.